So the introduction of the third dimension, the z-axis, of course requires us to have a third unit vector if we're going to report vectors in component form. And so we can see here we have the I unit vector that's running along the positive x-axis, the j unit vector that's running along the positive y-axis, and so now we're introducing the k unit vector that is running along the positive z-axis. So that just means that there will be three components for a three-dimensional vector in each of these three directions, x, y, and z, using I, j, and k. Now, we're not just going to limit ourselves to studying three-dimensional vectors in their component form. We're also going to want to know the magnitude of a three-dimensional vector. We want to know something about like the wind direction. We want to know what is the speed with which, what's the magnitude of that wind vector. So we have to be able to find that magnitude from the components. And so fortunately, we have a pretty seamless transition from 2 dimensions to 3 dimensions to use a 3D version of the Pythagorean Theorem. Now this is the one place where we're going to have to be able to draw things in 3D during this unit. Everything else we'll just do through visualization and such, but here we're actually going to have to sketch something. So what we want to do is we want to show that the 3D Pythagorean Theorem works. We of course know that the Pythagorean Theorem is a squared plus b squared equals c squared. So if we know the two legs, we know what the hypotenuse is. Well, the 3D version of that is a squared plus b squared plus c squared equals d squared. Meaning if I know the distance from one point to another in 3D space in both the x, y, and z directions, then I can square those, add those, and that'll equal the square of the actual distance. So I've kind of boldened out the x-axis popping out of the page at us, the y-axis and z-axis in the plane of the page. And so we're going to say that we're going to have a point ABC that's going to be a units. So we'll say like we'll count off 4, but really we'll keep it general to say that this distance here from the origin to that spot there is a units popping out of the page. We're then going to go 10 units in the y direction. So along the y-axis I'm going to count off 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are just arbitrary distances I'm traveling that I'm then calling a general distance of b or a or c, as we'll see in the z direction, just to give us a good picture that we can work with. But for the 3D effect, I need to kind of draw this out this way. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm right about here. So I've popped out a units in the x direction. I've traveled b units in the horizontal direction, but again to give that 3D effect of the xy plane popping out of the page at us. And then I'm then also going to travel 10 units up in the vertical direction. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we can kind of picture it, I've got this is my point A, B, C that is floating above the xy coordinate plane that is popping out of the screen at us. And so then the distance that we're interested in is this distance here, D, coming from the origin to this point that is floating above this xy coordinate plane that is popping out of the screen at us. Maybe if I add this line right here and kind of show that this is a right angle, so we've got a right triangle that we have created here. Now, we're trying to find D in terms of A, B, and C. We're trying to verify that this indeed is accurate. So this vertical distance here, we'll shift to blue just to kind of emphasize it. So that vertical distance right there is our z coordinate. It's the distance above the xy coordinate plane. So that is a length c. Now this diagonal here is not the a coordinate or the b coordinate. It's not the x coordinate or the y coordinate. It's some other distance. We're going to call it temporarily e. And so I have a right triangle here where I've got the two legs of my right triangle are C and E. So I'm going to say e squared plus c squared is going to equal my hypotenuse of this right triangle, d squared. So I'm just using a little Pythagorean theorem here to write essentially a Pythagorean theorem equation for this right triangle that is popping out of the screen at us. But I don't want to leave it with e squared. I want to change that into a and b. So what we're going to do now is we're going to see e as no longer the leg of this blue triangle. We're going to see it as the hypotenuse of this green triangle. And so again, this is a right angle here, since we're going out of the screen in the x direction and then making a 90-degree turn to travel in the y direction. So again, A is this distance right here. B, recall, is the distance that we're traveling in the y direction. So those are the legs of our triangle. So we can say a squared plus b squared is going to equal the hypotenuse, which is now this e right here, e squared. And so now I can use a substitution step. Since this e squared and this e squared are the same, I can go ahead and replace e squared with a squared plus b squared. And when I make that substitution, I end up with exactly what I was hoping for. A squared plus b squared plus c squared equals d squared. Or in other words, if I want to know what is the magnitude of a three-dimensional vector, I take the x, y, and z components of that vector, I square those components, I add them, and then of course have to take the square root, and that will give me the magnitude of the three-dimensional vector. So this means that finding the magnitude of a 3D vector is a pretty trivial exercise compared to what it could have been were it not that we had this formula. So it's no more difficult than it is to find the magnitude of a two-dimensional vector. We just have an extra component. Now for the direction, for an angle, that is something completely different, and we never really worry about it. We just say that the direction of a three-dimensional vector is embedded in the component form, because the question would become, from where do I measure the angle? Do I measure it from one of the axes? Do I measure it from one of the planes? It's not clear where the angle would be measured from. But for the magnitude, that's something that we can definitely calculate using our 3D Pythagorean theorem. This is a diagram that you will have to be able to recreate. You'll have to be able to derive the 3D Pythagorean theorem in the future.